Greetings, my name is 𝗧𝗜𝗦𝗜𝗧. I'm the Process Optimization Specialist for Lakeside Process Controls and Emerson Impact Partner. In this episode, we'll be talking about how to use Tuner to tune self-regulating process control loops. So we're going to cover how to read in the DAT files from collect. We're going to talk about windowing the bumps, identifying the bumps. We're going to review the bump summary, calculate the tuning parameters, and how do you save your workspace, and how does that relate to the tuning manager? So to read in the DAT files, pretty simple. You just click on the open file icon, read in file, and you pick the file you want to read. So first we want to read the output as it's outlined there. We're going to read in the PV next. This is for a flow controller. You can check the ranges, you can hit validate, and then validate again. Typically, you don't have to do much there. Here you can see that the time span is very, very wide. So what we're going to do is that we're going to zoom in. So you do a right mouse click, select X scale, and here we're going to select the origin to be around 17,200 second mark. And we're going to make the span 600 seconds wide. So you can see here we got a good span of the bumps. Everything looks good. The bumps do look very, very nice. Next thing we're going to do, we're going to do a bump, and then we're going to window. Actually, we're going to be working our way down that menu bar. So you click anywhere here, and then you want to size the window around the bump itself so that it encompasses the dynamics. And you click mark, and that registers it. Every subsequent bumps will be the same size as the previous. Here, that's fine. We're going to click on the next one. Here, we might just shorten that window a little bit. We'll click mark again. Same thing for that one, move it around. Maybe extend that one a little bit. Next one, going to adjust it as well. Maybe I want to extend it a little bit again. And that one there, we're going to extend it as well. Next thing we need to do is to identify the bump. So now we're working our way down the second part of that menu. Here you click anywhere on the workspace. So first of all, you got to look at your processes. You can see here you can tune for many different types of processes. For self-regulating is going to be a first order process. You click anywhere and you can see it fits a curve on the output and the PV. And see the little squares there? I call them little nubs. And you adjust the nubs to be able to fit the curve. And as you're adjusting it, you can see bottom left-hand corner, it's actually the numbers are actually process dynamic numbers are changing as you adjust those nubs. Once you're happy with it, you click register. Then you click on next. Do the same thing, click on the display. Output looks fine. We're going to adjust that to get a good steady state initial. Move the second nub to match the process dynamics. Once we're happy with that, we click on register. And we proceed with the next one. Likewise here. It's important here, if you want to make sure that your steady state initial and final are pretty good, that affects your process gain. Everything's good. We're going to do the next one. Here's not so pretty bump. So obviously here we're going to have to kind of adjust to see, make sure that it's, you see there, you got a steady state initial and after. We're going to register that. Got a couple of more. We're going to adjust that one. We're going to adjust this one here. That looks pretty good. Next one. Same thing. We're going to adjust the height, make sure we got a good average at the beginning and after. Maybe move that one to the right. We're happy with that. And there we go. So once you're done, it comes back to the next one. Next thing we want to do is review the bump summary. So we're working on a third of the menu item. There you can see you got all your results, you got your KPs. Now note your KPs are there in engineering units, not percent of span. You got your time delays and your time constant. Everything looks pretty good. Sometimes if you have one bump that may be a bit of an outlier, you can actually discard it. You click on discard, and that will exclude that particular bump test from the average. So everything looks good. Next thing we want to go to tune. Again, we're going to work our way down. Tuning parameters. There's all the information about the control loop. Process, you can assign a process if you want to. You don't have to do that. What that does is that it kind of compares your results to what typically should be for that type of control loop. Here we're going to select a hydraulic flow loop. Hydraulic means incompressible fluid as opposed to a gas. You can assign it here. You don't have to do that. Next thing you want to do, you see there your dynamics. Now they've been converted to percent of span. Actuator, again, you don't have to do this, but it may have impact if you want to tune your control loop more aggressively. Here we're saying it's a pneumatic valve, and we're saying that it's average, average meaning precise sizing and so forth. You can also select your type of controller. So if you're a Delta V user, you'll be using obviously Delta V, but you can see there you got different types of controllers for different types of DCS. You can create your own if you want to, if it's not listed there. But all different types of the major types of DCS. We're going to sign that. We're good. Everything's fine. Next thing is to choose a tuning rule. Now, usually I use the PZ. PZ stands for pole zero cancellation method. And once you accept that, you can see here it says, hey, you know what? Your time delay is a little bit outside the what we expect it to be. Your time constant is fine, but that's okay. Not a big deal. And typically, I default to pole zero cancellation method. There's a recommended lambda. Bottom right hand tells you recommendations. And you can click calculate settings, and there it has calculated your proportional and your integral. If you want to choose a different type of lambda, you could choose in, let's say, 6. You want to slow it down a bit, it will recalculate your tuning parameters. Next thing you want to do is tuning summary. But first, we're going to set up our path, make sure in your tuning manager. So if you get your tuning manager, you can set it up there. If it's not, if it does not exist, you can actually, it will create it automatically. Your data file, your workspace, everything else where it's actually all the files are going to be located. So that's just a verification. You can also set your preferences. You can set novice, intermediate. So novice, it just kind of just restricts you, just gives you the bare minimum. Or I'd like to go advanced. It gives you the default ratio and the default actuator class. You can change that as well. Next thing we go, now we're going to go to tuning summary. So you can enter your initials, your name there, and then run number. So then most important, actually, you can actually enter the as found tuning. So you make sure what it was before. Next, we're going to save a workspace. All that information will be saved in a workspace. And again, it's going to be saved in the file in the folder you selected. And it saves it as a BUP file. There it's going to say, okay, this is all the information we have. We're going to add the record. So what that does is that actually creates a database record of that, all the information in that file. So when you go to the tuning manager, so now you actually have a record for that flow loop, all the information for that particular time you tuned it, the controller, any kind of comments. So that's great to be able to come back to if you want to go do a control audit, or if you want to tune it a year later, what were the results then? So I hope you found that informative. The next video will be how to use Tuner for integrating processes. So note most of your loops are going to be either first order self-regulating processes or integrating processes. There will be other processes you can actually you can use, obviously integrating first order and so forth. Those are rare occasions. Here, pretty much 98% of your time, it's going to be either first order or integrating process. Thank you very much.